All right, so let's start with a little card trick, okay? And I think this one I might actually try to explain to you after it's done. Okay, so just an ordinary deck of cards here, okay? Nothing fancy, right? Just several, you know, just a deck of cards. And I'm gonna shuffle these, and then we're gonna do a little bit of thinking together, okay? So, okay, just kind of shuffle these a little bit, okay? Okay, so now I'm going to put a few cards out here, and I'm going to have some of you sort of pick them, and I'm going to be totally blind to the process, okay? So let's see, I'm going to do maybe like 6 cards. So 1, 2, 3, 4, 5, 6, okay? Like that, okay? And I'm going to have you guys actually pick out some cards. Okay, so let's see here. I'm going to have you guys pick out some cards. I'm trying to move these so that they're actually, oops, I'm going the wrong way. There we go. Okay, have you guys pick out these cards, and we're going to go from this direction. This is the right over here, okay? We go from this direction. So let's see, Zach. Okay, Zach up here in the front. Pick a card from the right. So tell me which card from the right you would prefer to have. The third one from the right, okay? And then I need someone else to pick out a card here. Sure, yeah. Remind me of your name again. Ivan, that's right. Kruger, yeah? Okay. Far left, okay? So look, I'm going to close my eyes, and I'm going to reveal these cards. Does that make sense? And then what I want you to do, okay, so remember, Zach, this was your card. Ivan, this was your card, right? What I want you to do is I want you to take the numerical value of the card itself, and I want you guys to like add them together. Does that make sense? Add the card's numerical values together. And by the way, ace is 1, and then 2, 3, 4, like the face value up to 10, and then a jack is 11. A queen is 12, a king is 13. Does that make sense? Okay. So I promise I'm closing my eyes. I'm not cheating here, okay? I'm closing my eyes. I'm going to show the cards one at a time, and then you guys can collude and do a little math problem where you add the values together, and then you're going to report the value, the total value to me. Does that make sense? Okay. I'm going to close my eyes and reveal this one. Okay, so can you see that? You got it? Okay, I think this was Zach's, right? That was Zach's. Okay. Okay, next one. Let me look. Here it is. Okay, close my eyes here. You got it, Ivan? All right. Okay. Can you add those two numbers together? Okay, add the two numbers together. So what do you have? 15. Okay. 15. Now here's the thing. There are lots of pairs of cards that could potentially add to those things. Does that make sense? A 10 and a 5, etc., right? There are lots of things that could potentially add up to 15. Okay? You telling me that value does kind of narrow the scope of options down, but I still am unable to sort of completely determine you know, just based on the information, the value is 15 what those cards are. But I'm going to do it anyways. Are you ready? So methinks that you have a, let's see, 15. Are you serious? Okay. That one's kind of tricky. I'm feeling like hearts are playing a prominent role here. Hearts, okay? And that you have a king and a 2. A king of hearts and a 2 of hearts. Is that correct? Yeah. Close enough. Okay, king of hearts and a 2 of hearts, okay? I don't know if that's very impressive, but it worked, okay? So king of hearts and a 2 of hearts, okay? So let's do 2 more, okay? And I mean, you know these two cards already, so maybe I'll kind of get rid of those. It was these two, right? Okay, let's kind of put those off to the side. Let's do another one here. Okay, so maybe, okay, you know, maybe Ava, you want to pick one out here? This one? And let's see, or somebody else want to pick one? Maybe Connor. Connor, you want to pick one? This one? Okay. All right, so I'm going to reveal these to you with my eyes closed. Okay, this one's yours, Ava. You got it? Okay. Then Connor, you got it? Okay, can you guys give me the numerical values of your cards? Well, not individually, but total. 11. 11. Well, okay. 11. Well, I feel like maybe 3 of spades and 8 of clubs. Is that true? Is that it? 3 of clubs, or 3 of spades and 8 of clubs. Is that right? Yeah. Okay, so there it is. Okay. You want to know how this works? Okay, it's sort of, because actually 11, there are lots of things that could have potentially added to 11, right? This trick is actually called little fibs. Little fibs. Okay? And here's the thing. Okay, let me kind of lay out the cards so you can see what's going on here. Okay, so I have an ace of clubs, I have a 2 of hearts, I have a 3 of spades, I have a 5 of diamonds, I have an 8 of clubs, and I have a king of hearts. You notice anything about those cards? It's the Fibonacci sequence. Do you know what I'm saying? It's the Fibonacci sequence. And it seems like, here's the thing, and I'll let you go think about this on your own, but it's true. If you think about it, the Fibonacci sequence arises naturally if you try to think about, okay, if I start with 1 and I start and I go to the next number 2, the next number 3, there's only one way I can get 3. It's going to be a 1 and a 2, yes? But then the problem is a 4, how many ways are there to get a 4? There are 2 ways to get a 4, right? What are the 2 ways you could get a 4? 2, 2, and 3, 1. Does that make sense? So you kind of skip over 4 on purpose because there's too many ways to get 4. Okay? So 4 is out. Okay? And then if you think about it, is there more than one way to get 5? Because 4 is gone, is there more than one way to get 5? No. So 5 can be part of the sequence. Okay? 6. Okay, 5 and 1 is one way that can happen, yes. Since the 4 is gone, 4 and 2 is out, but like 3 and 3 is out. Does that make sense? Could I have 6 if I have these 4 cards right here? Could I have 6 in this thing and still get away with it? What do you guys think? Why not? What are the 2 ways? 1 and a 5 and a 3 and a 3, yes? So really 6 is out because there are multiple ways to use kind of these first several Fibonacci's to make that work out. Now, if I only included 1 3, I could kind of get away with it. But I'm telling you, I'll let you think about this. The cards are systematically eliminated except for the Fibonacci sequence. Fibonacci sequence forces all previous cards in the Fibonacci sequence. There's exactly one way to get the sum of that one value. Does that make sense? Okay. So I knew right away when you said 11 that had to be made up of what? 8 and 3. Does that make sense? I knew when you said 15 that it couldn't be 10 and 5. It had to be 13 and 2. Yes? Now there's still the problem of, hey, what about the suits themselves? Well, it turns out you just kind of memorize those. Okay? And what I did is I used something called chaste ordering. So this is clubs, hearts, spades, diamonds. Chaste. C-H-S-D, basically. Yes? Clubs, hearts, spades, diamonds. Kind of a typical order that you use. You could also do alphabetical order if you really wanted to. Do you know what I'm saying? This is chaste ordering, and then I kind of just started it over again here, so this looks fairly random. The other issue is that you kind of put these 5 cards you want them to be on the top. Does that make sense? So you just do a couple of false shuffles. So that there was a slight sort of sleight of hand there. When I shuffled, I just made sure those cards stayed on top. Does that make sense? So that little trick is called Little Fibs. It's due to a mathematician by the name of Colum Mulcahy. Okay, you can kind of go look him up on the internet. He's sort of interesting guy. He's got a cool Irish accent. Okay, I think he teaches at Lafayette College or something. Okay, or actually no, Spelman College I think is where he is. Okay, all right, cool. Let's get to it here. So over here, let's share the screen. All right, so I'm going to ask you, what did you guys come up with on this one? What is this saying? What is this saying? There's no computers on this one, right? No computers. Any guesses? Yes. Yeah, that's right. So that's really, really close. So basically it's saying there is a student such that for all pairs of their friends, notice we're kind of making sure that Y and Z are not the same, right? All pairs of their friends. And how do I know they're friends? Because f of xy and f of xz, does that make sense? That means that x is friend with y and x is friend with z. And what's that y different from z? What in the world am I stipulating there? They're not the same person, right? So you're saying there is a Cedarville student that such that all pairs of their friends are not what? Are not friends themselves. Does that make sense? So like if you were to draw kind of the friend graph for this person, it would look something like this. Okay, this would be x. Okay, and you draw like a little edge between these things if they happen to be friends. Does that make sense? And I don't know, this would be y. This would be their friend z. And would I put an edge between y and z? No. So all of their friends would then be kind of coming off of here like this. You would get what we would call a star graph. Does that make sense? So essentially this little statement right here is just trying to describe this little star-shaped friend graph situation. Yeah? Okay, so good. Any questions on that? I think that's kind of neat. Yeah. Well, so the computer situation doesn't even enter into this one. I never used C, did I? Anywhere? Right, so the computer situation this is just completely different. I'm only talking about the friend relationship right now. Make sense? Okay, so no computers, no computers. Okay, other questions? All right, cool. Making progress here. Okay, so what about this? So this is for you to work on with someone next to you here, or by yourself, I guess, if you happen to be online or something. Translate this: the product of three negative integers is always positive, into a logical expression using that P of x is the statement x is a negative integer. Okay? X is a negative integer. So P of x is the open sentence. X is a negative integer. Does that make sense? So I want you to write this using like quantifiers and whatnot. Okay? The product of three negative integers is always negative, which you know is true. That's a true statement, right? But I want you to write that using logical symbols and just using this P of x thing right here. Okay? Okay, so think about that for a second. Okay, any ideas of how to start here? What are you starting with? How many numbers? 3. And you're saying something is true about all of them? So wouldn't it make sense that it would start out like this? For all x, for all y, right? I mean, look, honestly, we'll talk about the universe in a minute here, but and also for all what? For all z. Okay, what's true? Okay, and by the way, you want these things to be negative, correct? Okay, so what do? P of what? Well, actually, just P of x. Okay, and what? And P of z. What is that saying? It's saying for all x, y, z such that they're all what? Negative integers. So if they are all negative integers, then, which means I'm talking about an implication here, right? A conditional, implies what? Implies that their product is negative. How could I express that? P of x, y, z. Yeah? After all, x, y, z is just a number anyway. Does that make sense? So you're saying for any 3 numbers that are all negative, right? If they're all negative, then their product is negative, right? If they're all negative, then their product is negative. That's the essence of what we're saying. By the way, let me ask you, does the universe really matter here? Does it really matter what the universe is? No, right? I mean, look, if first of all, do I have to like be concerned about numbers that are positive necessarily? No, because the if part takes care of that automatically, right? So if like x were positive, then the if part would be false. Does that make sense? So the whole thing would be true anyways, yeah? The if part would automatically be false, so the then part wouldn't matter. It doesn't matter if it's true or false. The whole implication would be true. Yeah. That's right. So yeah, P of x is already automatically checking to make sure, right? It only is caring about those things that happen to be negative in the first place. Does that make sense? Yeah, that's right. You don't know that, right? That's exactly right. Yeah. It's checking that those things are negative. And it's saying, okay, are these 3 things negative? If they are, then their product is going to be negative also. Okay? Does that make sense? And again, the universe doesn't really end up mattering here. Sort of interesting, okay? Okay. So moving on. Okay. Here we go. Oh, there it is. Right. So, I mean, essentially, look, I said, use quantifiers to negate this statement. How would you negate, oh my goodness, how would you negate that disaster? Think about that for a second. So that's the statement we just came up with, right? And I'm asking you to sort of negate this thing and then to think about what you're saying in English. Yeah. You know how to negate it? Yeah, but okay, yes, that's one, yes, that's true, right? You just go like this, right? You go, not this disaster right here, yes? Not that, but I'm not gonna let you get away with that. You gotta tell me what, okay. So what is that as you know, in symbolic logic? So first of all, what do all those for alls turn into? Right, there exists an x, there exists a y, there exists a z. Basically, there exist numbers, there exists an x, a y, and a z such that what happens? Well, okay, so it's not this, right? So not, not this, not P of X and P of Y and P of Z implies P of X, Y, Z. Okay. How do you negate a conditional? Yeah. Okay, well, okay, so first of all, what is the opposite? Okay, let's just think about this. What's the opposite of, of P implies Q? Think about that. I say, if you get an A on the final, then you get an A in the class, right? If you get an A on the final, then you get an A in the class. What is the opposite of that? You get an A on the final, and you don't get an A in the class. Does that make sense? That's the logical opposite of that, right? So the negation of this is P and, like, you would consider me to be an absolute dirtbag liar if I said, if you get an A on the final, then I'll give you an A in the class. You would say, you did the exact opposite of what you said if you indeed did get an A on the final, and what? You did not get an A in the class. So P and not Q. Okay, so like negating this if-then statement, let's just kind of write this out. So there exists X, there exists Y, there exists Z. So look, the negation of this conditional, what is it going to be? Let's just say P of X and P of Y and P of Z. That's the P part, that's the if part, right? And what? Yeah, and not P of X, Y, Z. So what is this saying? This is saying, let's just kind of, I'm not going to write it out in full-on sentences, but let's just say out loud what this is saying. Someone already kind of said it, but let's just repeat it. This is saying there are numbers X, Y, and Z. There exist numbers X, Y, and Z that have what property? All three of them are negative, and yet what? And their product is not negative. The product is positive. Okay, is that a true statement or a false statement? This is false. Okay. Okay. Is that false? Well, but let's think carefully about this. Is that false? Is it for sure false? Is it ever the case that the product of three negative numbers is positive? Like if I'm talking about real numbers, though, no, it's not, right? So this is never the case in the real numbers, right? I'm just trying to make sure that we're on the same page. But Monique is saying, what about imaginary numbers? Well, what do you think about that? Does there exist an example in imaginary numbers where this sort of thing is true? What do you think? What about I times I? Remember what I is? I is like the square root of -1, right? I times, I don't know, -2 or something like that. Okay, but the funny thing is, how do we even, like I itself, like how can you talk about positivity or negativity when it comes to these imaginary numbers? Does that make sense? So when you multiply these things together, you do end up getting +2. But the problem is, how on earth do I even evaluate positivity and negativity for things that aren't real numbers? Does that make sense? Okay, that's a good suggestion. Okay, all right. Questions on that? All right, moving on here. Moving on up. Let's talk about the rules of inference. We're getting close to our goal of really trying to understand arguments that are valid, okay? All right, and this is where we're going to start using some philosophical terms. And I actually want you to know these things because I've just found that in my own experience, it's useful for me to know these like little Latin phrases. Plus people think I'm, extra special when I know things like, know these little Latin phrases. So QED stands for quod erat demonstratum, which means which was to be demonstrated, yes. Modus ponens is an argumentative style. And essentially what you should think about is the following. Basically, this is the if part right here. Okay, so this part right here is the if, right? So if this, then I want you to tell me what we can conclude from this. So basically you have P, and P implies Q. Okay, these are often referred to as the hypotheses or the premises, the premises. Okay, what can you conclude from this? Yeah. Yeah. Therefore, sometimes you use so therefore, Q. The thing you can conclude is Q. Okay? So P implies Q. If you know that's true, and you have P, then guess what you can conclude? Q. Okay, so I give you my ironclad oath. If you get an A on the final, then you get an A in the class. I'm saying that is my ironclad contractual verbal oath. And then you go and do your part and get an A on the final. What could you then conclude? Get an A in the class, which is the Q part. Okay? And this is a tautology, by the way. Okay? This is called modus ponens. It's a valid argumentative style. If I tell you that P implies Q is true, and I tell you that P is true, then you can immediately conclude Q. The fact that this is a tautology tells us it's a valid way to make an argument. What does tautology mean? If I did the truth table, what would I get all the way down? True, 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 true. Yeah? That tells you it's a valid argumentative style. So here I gave you another example. P is it is snowing. Q is I will study logic. I tell you, if it is snowing, then I will study logic. Okay, and then you say, it is snowing, therefore what? I will study logic. Yeah? Modus tollens. So first of all, modus ponens, right? Now, modus tollens. Okay, look at that. So again, we kind of start with P implies Q. Okay. And what else do we start with our premises? Not Q. And one thing you might want to remember is that P implies Q is actually equivalent to not Q implies what? Not P. Okay? So me saying to you, if you get an A on the final, then you get an A in the class, is equivalent to me making the contractual oath. If you don't get an A in the class, then what? Then you didn't get an A on the final, okay? Those are logically equivalent to each other. So what can we conclude here? Therefore what? A little triple bubble thing right there is often the symbol used for therefore. Therefore what? Not P. Yeah? Okay, so there it is. And this is a tautology. You can check it out if you went into the truth tables, and you could convince yourself that it's a tautology, which means it's a valid form of argument. Oftentimes this is referred to, it's modus tollens is the Latin phrase for it, but oftentimes this is referred to as a contrapositive proof. Contrapositive proof, or a proof by contraposition. You assume the opposite of the conclusion, and you work toward the opposite of the premise. Okay? So if it is snowing, then I will study logic. I will not study logic. Therefore, it must not be snowing. Yes? Any questions on that? Those are probably the two of the most important argumentative forms. And basically, modus tollens is really just the same as modus ponens. Do you know what I'm saying? Do you see why? It's because this thing right here, P implies Q, is really the same as not Q implies not P, right? It's equivalent to that. And therefore, this is really just modus ponens in disguise again. Yes? So modus tollens is really just a reimagining of modus ponens. Okay? Questions on that? Okay? This is one we've looked at before. hypothetical syllogism. What? P implies Q. Q implies R. So those are the two things we know. Therefore, what? We know P implies Q is true. We know Q implies R is true. Therefore, P implies R. Remember we kind of encountered this before? We actually thought that P implies Q and Q implies R is logically equivalent to P implies R. But what was really going on is in your mind, you were saying, oh, I can just conclude P implies R from here. Okay? I'm able to conclude that P implies R from here. It's like a little electric current has gone from P to Q to R. Does that make sense? P implies Q, which in turn implies R. Okay? P is it snows, Q is I study logic, R is I get an A. If it snows, then I study logic. If I study logic, then I get an A. Therefore, if it snows, I get an A. You can kind of skip over that little intermediate step. Yeah? Okay? And that is a tautology as well. I promise this is actually also itself a reimagining of modus ponens. I won't tell you how, I'll let you kind of think about that, but it actually is. All of these can basically be reduced to modus ponens. Okay? So this is hypothetical syllogism, stringing together these conditionals. Okay? Any questions on that? Okay? Disjunctive syllogism. Why is it called disjunctive syllogism? Look, we have P or Q, and what else do we have? Not P, right? It's disjunctive because you have an or right here. Does that make sense? Yeah? Disjunctive syllogism. Okay, so look, here, look, what if I said to you, and look, I'm telling you, you guys know all of these. If I said to you, I am either left-handed or right-handed. I am not left-handed. Therefore, I am right-handed. Does that make sense? That's disjunctive syllogism in a nutshell. You kind of have this binary thing. I'm either this or I'm that. Well, I'm not this, therefore it has to be the other thing, yes? If I know that the or part is, the or is actually true. Therefore, what's the conclusion? Q. Right, Q has to be true. Okay? I will study logic. I will study English lit. Okay? I will study logic or I will study English lit. I will not study logic. Therefore, I will study English lit. Yeah? That's what's called disjunctive syllogism. Here's something that's kind of interesting, y'all. Remember, we said that P implies Q. What's the negation of P implies Q equivalent to? We just talked about this a little bit ago. What's the negation of that? P and not Q, right? Yeah. So what about P implies Q? That would be equivalent to the negation of P and not Q, which in turn is equivalent to, think about it, if I used De Morgan's law, what would that be? Not P or Q. You see that? Yeah? So not P or Q. Okay, now I'm going to leave it to you to see why, okay, P implies Q is actually equivalent to not P or Q. And I'm going to leave it to you to see why this is once again just a reimagining of, what do you think? Modus ponens. It's a reimagining of modus ponens. Yes, Monique. Well, if I take the not of the not, right? What's not P implies Q? That's just P implies Q. That's what I have written over here, yes? I just took the not of both sides. Does that make sense? Not, it's kind of like a negative or something. Okay? So I promise this little equivalence we just wrote down here can get you back to modus ponens once again. Okay? if you think about it for a minute. Actually, modus, it can get you back to modus ponens once again. Okay. In fact, it's pretty easy to see that this guy right here, P or Q, that thing is equivalent to not P implies Q. Yes? P or Q is equivalent to not P implies Q. Therefore, what am I really doing here? I just gave away the farm. Look at not P implies Q, not P, therefore what? Q. Which argumentative form is that? It's really just modus ponens. Do you know what I'm saying? I just have a not P instead of a P. Okay. Interesting. Okay, so now here, these ones I'm about to talk about that we'll finish with are all kind of stupid. They're obvious. Okay. Look, if I have P, can't I clearly conclude P or Q? If I know P is true, isn't P or Q automatically true? Yes? Okay. I will study logic. I will visit Las Vegas. Okay. I will study logic. Therefore, it's valid to conclude that I will study logic or I will visit Las Vegas. Like the visit Las Vegas part, who cares, right? I already said I was going to study logic, right? But this is interestingly something that comes up fairly often. I don't care about you knowing these latter ones as much. Really what I want you to know is disjunctive syllogism, hypothetical syllogism, modus tollens, and modus ponens. But there's one more I'll want you to know here in a minute. But addition is fairly trivial. You know what I'm saying? Simplification. If I know P and Q is true, can't I conclude that P is true? Yeah? Because if P and Q is true, what does that mean about both P and Q? They're both true. Okay? That's called simplification. This one's sort of stupid. Look, if I have P and Q, it's sort of funny to try to write this with an implication. P and Q, what can I conclude? Therefore, what? If P is Q and Q is true, what can I conclude? P and Q. Yes? That's what I'm trying to articulate right here. Okay? That's why I put weird parentheses everywhere. Okay? That's referred to as conjunction. I'm kind of putting them together in the form of an and. Okay? This one's tricky. And this one I want you to know, it's called resolution. Okay? Basically this, not P or R, P or Q. And I'll let you kind of think about this. Why is it that you can conclude Q or R from here? Okay, so you basically have P and its negation in each one of these first two steps. And you're able to conclude Q or R from there. Think of an example. And I think you'll convince yourself as to why this is true. By the way, this comes up in computer science a lot. You can actually easily simplify really complicated statements by using resolution over and over again. It's a very important one. Okay? And I think I'm going to stop right there. So go to Chuck's and figure out come up with an example for why this actually makes sense. And by the way, on Friday, a lot of you have formed some groups and have kind of carved out some chapters to present on. On Friday, I'll actually present again. I'm going to present on the incomparable Archimedes and his determination of the formula for circular area. Okay, which will be a nice little lesson in geometry again. All right, that's it.